Okay. Maybe let's get started then, since we have all the committee members here. Let me do a short introduction about Will. Will joined my lab after finishing undergrad from UC San Diego. Well, I would describe Will as very flexible on the project, what he would like to work on. I remember he come to my lab wanting to work, or I asked him, I said, hey, what are you interested in? He said, well, topological insulators. I said, that's great. So I snapped him in. So by reality, I already have a plan, wanting to have guide him into the direction to work on batteries. And then later, so he's using a lot of electron microscopy. So he just didn't know that yet. So, but turned out to be that's a good transition into the electron microscopy. He has been playing a very important role in my lab to building up the TEM expertise and looking onto the battery problem. So I'll let him to tell you more about that. But let me mention, another thing about Will. Will is a good heavy drinker. Drinking with him is really a lot of fun. Well, that was before COVID-19, right? So during COVID, we haven't really done that. There's something very interesting about Will. I think Will knows how to speak Mandarin, but he never speaks Mandarin with me unless he's drunk. He only speak in Mandarin. Will, am I right? I think if my memory is still right, I think you are the person, drinking can switch you in language. Well, with that, I will let Will telling you about what he has been doing.
All right, yeah, thank you, Yi, for the introduction. Yeah, so like Yi said, I'm Will Huang, and you are at my PhD defense titled Cryogenic Transmission Electron Microscopy for Next Generation Batteries. So batteries are extremely important for our clean energy future, mainly through the electrification of transportation. So by switching from combustion vehicles to battery electric vehicles, we can significantly reduce our greenhouse gas emissions. But the adoption of these batteries, or the adoption of these electric vehicles, is held back mainly by the range of current electric vehicles. That's in part due to the relatively low energy density of the modern lithium-ion batteries used in these electric cars. So to address these shortcomings, we need to develop new high-energy battery chemistries. But to understand how we can actually improve the battery energy density, we need to understand how these batteries work. So the lithium source within the cell in a modern lithium-ion battery is the cathode. All the lithium comes from the cathode, which is generally a lithium transition metal oxide, such as the LCO, or lithium cobalt oxide, shown here. And the discharge state, the lithium is all in the cathode. Now on charge, lithium ions move through the electrolyte, which is typically some sort of liquid that conducts only lithium ions, and inserts itself into the graphite anode, where lithium ions are stored between sheets of graphene. And by moving these lithium ions back and forth between the cathode and the anode, electrical energy can be stored and released on demand. Now, these modern lithium-ion batteries have energy densities of about 250 watt-hours per kilo. But by switching to anode materials that can store more lithium, such as silicon or metallic lithium, we can further increase our energy densities beyond 250 to about 350 with a silicon anode, and by moving beyond lithium-ion batteries in excess of 450 watt-hours per kilo. But doing this sort of, by implementing this sort of high energy density battery chemistry is not trivial. And this is mainly due to the lack of understanding of a structure within the battery called the solid-electrolyte interphase, or SEI. And this SEI is a film that forms on the anode surface due to electrolyte reduction at the anode potentials. Now, lithium-ion batteries among electrochemical devices are fairly unique in that they operate outside of the stability window of the electrolyte. So what the SEI film does is it passivates the anode electrolyte interface to make the interface metastable. So this SEI is extremely important because it dictates the stability of the anode and the whole battery itself, but it also mediates ion transfer between the electrolyte and into the anode material while blocking further electron transfer. So many scientists in our field have spent significant effort in trying to characterize and understand the SEI in order to build better batteries. And people typically think of the SEI as a sort of a surface film on the anode. So surface analytical techniques such as X-ray photoelectron spectroscopy, or XPS, have been the go-to characterization method in the field. And XPS has very good spectral resolution, but very poor spatial resolution. But still, people have used this technique to identify the components within the SEI, mainly lithium, fluorides, oxides, and carbonates, and built models of the SEI structure from XPS, which typically is thought to consist of a mosaic of these different phases. But since XPS doesn't offer any spatial resolution, the heterogeneity among these phases isn't really well understood. For example, are these grains of lithium oxide at the nanometer scale or the micron scale? And for this kind of analysis, the go-to technique in the field of material science is the transmission electron microscope, or TEM. And the TEM offers high-resolution structural and chemical information down to the atomic resolution. But doing this sort of TEM analysis on battery materials is non-trivial. That's because lithium and similarly lithiated compounds are air reactive and weakly bonded. So that means that during sample insertion into the TEM, during the brief air exposure, battery materials, such as this piece of lithium, will corrode with air and water. And that compromises any of your interesting chemistry as you instead form lithium oxides and hydroxides. Attempting to do any high resolution imaging of the specimen results in holes being drilled in your sample from the electron beam damage. Now in structural biology, biomolecules are even more sensitive than lithium. But in 2017, the Nobel Prize in Chemistry was awarded for the technique of cryogenic electron microscopy, or cryo-EM. And what cryo-EM can do is it can stabilize these very sensitive biomolecules under electron radiation. So colleagues in our group, inspired by this technique, have adapted this method for battery materials, where by opening lithium metal or other lithiated compounds in the glove box and freezing these specimens under liquid nitrogen, we can actually stabilize these specimens under the electron beam and kinetically freeze out any side reactions. And using this technique, our group was able to stabilize and image the lithium metal along with its atomic lattice. And now, using this technique, our group, we can now image and preserve battery materials and their SEIs with high resolution. So using this technique, the goal of my PhD has been to develop new insight and understanding into the SEI of various systems. So here we'll talk about my work looking into the role of electrolyte additives in stabilizing the silicon SEI. Then looking beyond lithium ion chemistries, how can we refine the structure of the SEI on lithium metal? And finally, how does the SEI on lithium affect its calendar aging stability? So firstly, silicon anodes, they're currently being developed by a lot of different companies, including Tesla, for next generation lithium ion chemistries beyond pure graphite anodes. So silicon is very attractive not only due to its high lithium storage capacity, but also its low materials cost. So silicon is extremely abundant within the Earth's crust. If we look at the lithiation reaction of silicon, we can see why silicon is so attractive. So for graphite, for the conventional graphite anode, it takes 6 carbon atoms to store a single lithium ion. And that's the graphite intercalation reaction. For the silicon alloying reaction of lithium, a single silicon atom can store 3.75, so almost 4 lithium ions. And what this means is that this gives rise to a gravimetric capacity of about 10 times more than that of graphite for silicon. But the problem with the silicon anode is that high lithium storage capacity results in high volume expansion. And that exposes new surfaces for SEI formation during each charge and discharge. And after many cycles, this SEI grows very thick and resistive and starts to consume a lot of lithium ions. So now the question we have is, using cryo-EM, what kind of new insight can we start to gain into the silicon SEI. So to carry out this sort of experiment, we need a clean silicon surface to lithiate and grow an SEI on. And silicon nanowires grown directly on a TEM substrate are ideal because they're electron transparent, high quality, and single crystal with a thin native oxide layer on the surface. So it's very similar to a real silicon anode material. And this work was done in collaboration with Michael Braun from Paul McIntyre's group. And what this means is this results in a silicon system that can then be lithiated in a real coin cell and prepared with minimal sample processing and high throughput. And because of this, we don't need to use any additional binders or conductive additives that are commonly used in real battery composite electrodes, which only serve to further complicate the system. With this test platform, we can then start to answer these unsolved questions for the silicon anode. So it's known in the field that the stability of lithium-ion batteries depends very critically on the electrolyte composition. A common electrolyte formulation used in lithium-ion batteries consists of a blend of ethylene carbonate, so a cyclic carbonate, EC, along with a linear carbonate such as diethyl carbonate or DEC. And graphite anodes in this formulation alone, along with a lithium-containing salt, will cycle pretty well. But for silicon, there's an additional critical electrolyte additive, and that's a fluorinated ethylene carbonate, or FEC. And it's widely known in the field that with the addition of this FEC additive, so here this is with the addition of 10% FEC electrolyte additive, the capacity retention, so this curve down here, of the silicon anode and its lifetime is greatly extended. But at the same time, the first cycle efficiency of the silicon anode, which measures the amount of lithium you can insert into the structure and then retrieve back on the delithiation cycle, half cycle, decreases when FEC is added. So the question now is, with cryo-EM, can we figure out what this electrolyte additive FEC is doing to stabilize silicon, and what are the origins of these effects? So we can take our silicon nanowire platform that we've developed, and then we can fully charge or lithiate the silicon nanowire and prepare it for a cryo-TEM analysis, as shown here. So this image here is actually the first high-resolution image of lithiated silicon and its SEI ever recorded. So this probably looks like mostly just gray, but down here what we can see is that we have a crystalline lithium silicide core. That's this lithium-15 silicon 4 phase, which is the most lithium-rich phase for the lithium silicon phase diagram. And out here is vacuum. But in between here is the SEI, which is what we're interested in. And this is all in the electrolyte without any FEC additive. If we then zoom in on the SEI, we can see that there are crystalline lithium oxide domains along with a lot of amorphous components. And these amorphous components are coming from the lithiated silicon oxide, so lithium silicate, along with LEDC, so that's lithium ethylene dicarbonate. And this lithium ethylene dicarbonate is an organic carbonate that comes from the reduction of ethylene carbonate, the solvent. Now, high-resolution TEM images like the last image are sensitive to crystalline components, but the amorphous boundaries are harder to visualize. But like we mentioned before, the TEM is a good spectroscopic tool. And by operating the TEM in scanning TEM mode, or STEM mode, coupled with electron spectroscopy methods like electron energy loss spectroscopy, or EELS, which is very nice because it's sensitive to light elements like lithium, we can start to map out these boundaries in these lithiated silicon nanowires. So this dark field image down here shows strongly scattering regions in the core coming from the lithium silicide, along with a dense oxide layer, and then a lower density surface layer. Lithium intensity is strongest in the lithium silicide core, with a dip in intensity in the lithium silicate layer due to the low lithium concentration in lithium silicate, and then another enrichment in the SEI layer. The electrolyte reduction is also reflected in the carbon signals on the outer surface coming from the organic carbonates, and then the oxygen is enriched on the outer surface due to the lithium silicates along with the organic carbonates. But what's really interesting then if we take these silicon nanowires and then delithiate them. So if we take the nanowires through a full cycle, we can see that lithium is removed not only in the silicon core, but also along the outer surface where the SEI is. Additionally, the carbon counts across the nanowire become very dilute across the nanowire surface. And all of this suggests that there is some reversibility to the SEI on this first cycle. So people generally think of the SEI as sort of a statically growing or monotonically growing structure. But from this kind of TEM analysis, we can already see that the SEI is a lot more dynamic than that. And it can even exhibit some reversibility on this first cycle. Okay, but so what we really are interested in is what the electrolyte additive FEC is doing and why it's so important for silicon stability. If we then do the same kind of experiment, lithiating the silicon nanowire, now in this electrolyte with 10% of this FEC additive, we can see that there are changes to the silicon nanowire. So the lithium silicide core remains the same. So the lithiation behavior of the silicon itself is not changing, but the SEI nanostructure is changing significantly. Whereas previously without FEC, we saw lithium oxide in the SEI. Now we're seeing a completely amorphous SEI. So that tells us the lithium oxide is coming from the ethylene carbonate reduction. FEC is reported to defluorinate during its reduction into a vinylene carbonate radical, along with lithium fluoride. And what we're seeing here is the organic FEC reduction product, which is a polymerized vinylene carbonate along with the amorphous lithium silicate. And we can again do the STEM EELS mapping and see that a dense, thick, organic-rich SEI is forming on the silicon nanowire surface. And notably, there isn't really any fluorine in this SEI, which further reinforces that the defluorinated FEC is polymerizing into a poly-VC polymer onto the silicon surface. And on delithiation, we can see large differences as well. The lithium remains enriched in the SEI layer along with the carbons, suggesting that this organic SEI, this poly-VC layer, is very stable on delithiation. And for comparison, these are the two electrolyte systems. Up here is without FEC, down here is with FEC. And we can clearly see that the SEI is changing radically on the, or there are significant differences in the SEI behavior on delithiation on the silicon surface. And that the SEI with the FEC additive is much more stable than without. So in EELS, in this kind of STEM EELS mapping, we also have access to the raw spectra. And EELS is a very powerful technique because we're also sensitive to the bonding states as well. Looking at the carbon K edge, we can see there are strong carbonate peaks in the SEI on lithiation, that then oxidize away on delithiation. With the addition of the FEC, these carbonate peaks remain robust on both lithiation and delithiation, suggesting that the polymerized FEC product is contributing to the stability of the silicon anode. And so to briefly recap this work, using cryo-TEM, we can track the evolution of the silicon anode across the entirety of this first cycle. And we can see that the EC reduction product, the LEDC component, is electrochemically unstable on the silicon surface during the delithiation step. But with the addition of the FEC, this poly-VC reduction product is very stable, both electrochemically and mechanically, and remains protective of the silicon surface. And this likely leads to that worse first cycle efficiency we see with FEC, but it also stabilizes silicon and extends its cycle life. Okay, so silicon anodes are already being used in advanced lithium-ion battery chemistries. But beyond silicon, the ultimate anode material is actually elemental lithium or lithium metal. So silicon can store a lot of lithium ions, but it also incorporates some dead weight from the silicon host lattice itself. But for the highest lithium storage capacity, elemental lithium is pretty much impossible to beat. And if we can make lithium metal work, we can start to replace these graphite and silicon anodes to push the classic transition metal oxide chemistry to even higher energy densities. But it also opens the door for new cell chemistries, such as lithium sulfur and lithium air, that don't have lithium in the cathode. And these new chemistries can potentially start to approach the energy densities of gasoline. But similar to silicon, lithium metal implementation is limited by the understanding of the SEI. So the first demonstration of cryo-EM by our group allowed us to look at the lithium SEI, which actually looks fairly similar to this original model this classic model of the SCI that was proposed back in the 90s. But it also introduces some new questions. Specifically, the lithium oxides and the lithium carbonates within the SCI do match this model, along with the organic materials that are presumably the organic carbonates and other polyolefins within the SCI. But one missing component in the SCI is the lithium fluoride component. And this is important to understand, even though it's just one component in the SCI, because in the literature, it's widely believed that this lithium fluoride is critical to the battery cycling stability. And a lot of high performance anode chemistries rely on these purported fluorinated SCIs. So a significant knowledge gap is now opened in the field, which is where is the lithium fluoride in the SCI? So to address this knowledge gap, we'll carry out this experiment on the lithium metal SCI using the same fluorinated electrolyte system that we used previously for silicon. And that's this ethylene carbonate diethyl carbonate electrolyte with the 10 volume% FEC additive. And similar to silicon, with the addition of the FEC additive, we can further stabilize the lithium metal cycling shown here. And this is commonly attributed to this defluorination reaction, generating a lot of lithium fluoride in the SCI. If we then carry out this sort of conventional XPS depth profiling of the SCI on the lithium metal in this electrolyte, we can see that there's an outer surface that's rich in organic materials, and then an inner surface that's rich in lithium fluorides and other inorganic materials. And this results in this kind of classic SCI model where we have this bilayer structure of this inorganic lithium fluoride and lithium oxide rich inner SCI layer with a more organic outer SCI layer. So we can then prepare a similar TEM sample of lithium metal in this kind of electrolyte. And here we can actually plate lithium metal directly on the TEM grid, so we don't need to grow any kind of nanowires. And lithium naturally plates as these kind of nanoscale filaments, which is very convenient for TEM analysis and sample preparation. But looking at the cryogenic high resolution TEM of the SCI in this system, we don't see any lithium fluoride in the SCI. We can see lithium metal down here, and what we're mostly seeing are amorphous organic materials along with lithium oxides in the SCI. This Fourier transform here takes the, converts all the spatial information here into frequency information. So all these spots correspond to lattice spacings in the image. And we can see that there's a variety of different lithium oxide orientations, but no lithium fluoride as well. But this mode of TEM imaging is highly sensitive to crystallinity. So if lithium fluoride were in principle amorphous, we would not be seeing that. So instead, we can turn to STEM EELS mapping again, where we're insensitive to crystallinity and instead picking up chemistry. And what we see is that this SCI layer on lithium, it's rich in oxygen, but it doesn't have any fluorine signal. And that tells us that we don't have any amorphous lithium fluoride within this lithium metal SCI film. And by the way, we don't see this inner fluorine-rich SCI. And the term that people commonly use in literature for this this kind of thin films on this thin film SCI on the lithium surface is the compact SCI. So if lithium fluoride isn't depositing in that compact SCI, but it's being detected in XPS, then that tells us that lithium fluoride is depositing somewhere else on the electrode. So to do this, we can form an SCI on a model substrate, one that captures the SCI all across the electrode, similar to what we're seeing in XPS. So to do this, we use a carbon film membrane on a TEM substrate as a flat surface and a conductive surface. And then we can form an SCI on this flat conductive membrane without plating any lithium, and that keeps the surface area low. So we can form the SCI and then put it in the TEM, and we can start to map out a lot of really interesting SCI features beyond this compact SCI film. So all across the electrode, actually, what we're seeing is that without any lithium plating, or independent of any lithium plating, we have these particles of SCI precipitating. And these particles are rich in lithium, oxygen, and fluorine. And these particles are discrete, they're not a film, and they're tens of hundreds of nanometers in diameter, but exist across a micron length scale. And looking closer at the actual nanostructure of these SCI particles, we can see that they have a heavily fluorinated core along with a more oxygenated shell, creating this sort of core shell morphology. From the fluorine spectra, we can see that the core is lithium fluoride, with this outer shell consisting of lithium oxides and organic carbonates. And these bilayer structures could be what's giving rise to this sort of outer organic, inner inorganic SEI structure from XPS. Looking at this in bright field TEM, we can see that this is out here is this outer, more soft organic material. And looking from the electron diffraction, we can further confirm that these are lithium fluoride particles. And it is polycrystalline, although there is a heavy preference for a preferred orientation, along with more random orientations of lithium oxides as well, which matches what we see in the stem eels. So based on these previous observations on that sort of model substrate, we can start to see that these lithium fluoride particles are actually quite dilute. And then if we were, once you plate out lithium metal, you increase the surface area of your electrode dramatically. If we map enough of these lithium metal filaments, which are much higher in surface area, we can then see these dilute lithium fluoride particles if we map enough surfaces. And based on these dilute natures of these particles, where there's only single particles across microns of length of lithium, we can start to see that these lithium fluoride particles likely contribute very insignificantly to ion transport across the electrode. And from this sort of relatively simple study, we can already learn a lot about the SEI. First, we can see that XPS can detect the chemistry of the SEI fairly well, which is what it's designed for. But for detecting SEI structure, it's fairly ineffective. Only using a high resolution method, such as this cryo-TEM method, can we start to get accurate pictures of the SEI on these battery materials. We can see that there's this whole new regime of the SEI beyond this compact SEI film, where these inorganic lithium fluoride particles are sparsely decorating the electrode surface rather than incorporating into the SEI film. And finally, we can see that for this FEC additive in particular, it's the organic components that incorporate, while these inorganic fluorinated products precipitate outside. And that means they likely contribute less to the actual lithium cycling stability. And from a general design perspective, it then seems like the fluorination of these electrolyte additives likely aids in their reduction, but may not necessarily provide direct electrode protection. So the previous electrolyte system of lithium metal with this FEC additive is an improved electrolyte system, but it is still fairly primitive for these lithium metal chemistries. Recently, what we've been seeing is in academic literature, new electrolyte formulations have increased the viability of these lithium metal batteries significantly, with groups here at Stanford developing new solvents, such as this FDMB solvent, which can then enable 100 cycle lifetime in an industrial pouch cell format for a lithium metal battery. Or this work out of Dalhousie University, where a borinated dual salt electrolyte can then enable 90 cycle lifetime. Outside of academia, startup companies like QuantumScape can show very impressive cycle lives as well, which makes lithium metal seem more viable in the near future. But cycle life among different battery metrics is just one part of the picture. And that's especially important if you, and other metrics are also extremely important, especially if you're targeting the electric vehicle sector. So according to the AAA, the average American spends about 50 minutes a day commuting. So if you look at this from the reference frame of the vehicle, that means that most of the car's lifetime is spent at open circuit, so not cycling, which is then reflected in a different metric that's called the calendar life of the battery. So the question now for lithium metal is, as the cycle life improves, how does the calendar life or calendar aging of the lithium metal battery compare? So in collaboration with David Boyle, another student in our group, what we did is a fairly simple measurement of the capacity loss of lithium metal during storage. So across a variety of different lithium metal electrolytes, some of which are good at cycling, including this FDMB electrolyte, shown previously in this dual salt electrolyte. And some are also bad at cycling, such as these more primitive carbonate-based electrolytes without any FEC additive. What we did is we measured the cycle efficiency of all these different electrolytes on the second cycle with and without a 24-hour storage step in between. So this black bar here is the average Coulombic efficiency, with higher being better. This blue bar here is the second cycle efficiency if there is no rest step. And this orange bar here is the second cycle efficiency if you include a 24-hour storage period. Now we can see, and this delta CE value here measures the drop in lithium efficiency, cycling efficiency when you include this storage step. And what you can see is that there are bad cycling electrolytes with better storage efficiency, along with good cycling electrolytes with moderate to bad storage efficiency. But the two best electrolytes in the literature, this dual salt and this FDMB electrolyte, having fairly bad storage stability. If we extend the storage time out to a week, the capacity loss compounds with the initial 2% loss in the PF6 chemistry and the FSI in FDMB chemistry, turning into 6%, and the initial 6% in this lithium perchlorate chemistry, further compounding into 15% loss. And by further increasing the temperature as well, the storage loss gets even worse. At 60 C, this PF6 in carbonate drops from the relatively good value of 1.8% down to 15.8%. And just for reference, what we're seeing is 2 to 7% storage losses in 24 hours. But a good lithium ion battery, even stored at 40 C, will only lose 2% capacity in a year. So even the most stable electrolytes, such as this one, are overall very terrible. So the question now is, what is the origin of this loss and why does it happen? So again, we can turn to cryo-TEM and start to look at the lithium metal SEI before and after this 24 hours of storage. And what we see is that this thin, about 10 nanometer thick compact SEI on lithium metal further grows into thicknesses in excess of 30 nanometers. And this thickening is sometimes very highly non-uniform as well. By taking a lot of measurements, we can start to get statistics on this thickening trend, and we can see that the growth is indeed highly irregular. And these measurements are all for this LiPF6 in ECDEC, which is a fairly bad electrolyte at cycling, but among the better ones at storage. But what we see is if we look at these other electrolytes, including this dual salt blend that's good at cycling, and this lithium perchlorate in carbonate, which is both bad at cycling and bad at storage, this kind of trend in this compact SEI film thickening is universal. And this type of compact SEI growth, where you have this slow thickening of this SEI film with time, is fairly in line with traditional models of SEI growth and have been predicted and measured in literature using other techniques. But the thickening of that compact SEI isn't really the whole story for lithium metal. So zooming out to capture more of a micron length scale, we start to see deposition of large SEI particles along the lithium surface, which we call extended SEI due to their larger length scale. So the SEI is typically thought of to exist at the 10 nanometer length scale, but here we're seeing hundreds of nanometers of SEI particles. In these dark field STEM images, the bright spots here are the heavier, larger SEI particles, and these light rods are the lithium metal filaments. And we can see these SEI particles exist both in these bad electrolytes along with this good electrolyte. Looking at the chemistry from eels, we can see that there are differences in all of these different extended SEI growths in different electrolyte chemistries. So here in lithium perchlorate, which is bad at cycling and also very, very bad at storage, the extended SEI is rich in carbons and oxygens. Whereas in the LiPF6, which is bad at cycling, but better at storage, the extended SEI is rich in carbon, oxygen, but also this fluorine coming from the LiPF6 salt. And in the dual salt borinated chemistry, so this is this BF4 and DFOB salt, we can see that the extended SEI is mainly rich in carbon, oxygen, and fluorine. But the boron's primarily regulated to this compact SEI film. But universally, all these lithium metal electrolytes are bad to varying degrees during storage, and all of them do show these extended SEI growths. Looking closer at the lithium perchlorate system, which shows the worst storage performance, which loses about 7% capacity in 24 hours, we can see that there actually isn't any chlorine signal in the extended SEI shown here. Instead, there's only carbon and oxygen, along with some lithium. From the carbon K edge, this extended SEI is mainly organic carbonates, meaning that this significant extended SEI deposition is coming from the continued reduction and precipitation of the electrolyte solvent. In comparison, this LiPF6 system, which only has the salt anion, the perchlorate swapped out for a PF6 anion, shows much less storage loss, only about 2% in 24 hours, along with an extended SEI that, based on the fluorine K-edge chemistry, appears to be rich in lithium fluoride. In addition to this inorganic lithium fluoride component, there still is some organic deposition products coming from the solvent, and that's coming from the that's indicated by the carbonate peak along with this carbon hydrogen peak as well. And from this, it appears that the presence of this fluorinated species helps reduce the runaway solvent decomposition that we saw previously in the perchlorate case. So even though we showed previously that the lithium fluoride is very dilute and probably doesn't impact lithium metal cycling significantly, it does still appear to benefit the storage stability of lithium metal. And so from all of this, it appears that these subtle SEI chemistry changes can significantly impact the storage performance of these different lithium metal systems, mainly by affecting the rates or the degree of the SEI growth. But beyond the SEI chemistry, the lithium microstructure, shown here through SEM images, also plays a large role. So in these pore cycling lithium systems, like the PF6 and the perchlorate in the ethylene carbonate, we can see that lithium plates in this kind of filamentary or more wiry structure, which is going to have a very high surface area. While in the better cycling systems, such as the dual salt borinated chemistry and this FSI and FDMB developed here at Stanford, lithium plates in this more kind of thick or pillar-like microstructure. And these large lithium deposits, they reduce the lithium surface area, but at the same time, what we see in these coulometry measurements is that the amount of capacity loss is similar or worse than some of these high surface area chemistries such as PF6 or perchlorate. And it tells us that these electrolyte systems, even though they have much lower surface area, are actually more reactive than this PF6 in carbonate, for example. So for the field, that tells us that we need to optimize these two factors to ensure long calendar life lithium metal anodes. And that's the surface area of the lithium deposition, along with the rate of SEI growth per surface area, or basically the reactivity of the lithium surface to the electrolyte blend. And from measuring these existing electrolytes, we can start to classify them or group them into different categories among these two metrics. So we can identify fast corroding high surface area systems, such as the perchlorate in ECDEC, and these are going to have the worst storage stability out of anything shown here. We can also identify high surface area chemistries, but with slow corrosion kinetics. For example, this PF6 in ECDEC, which is fairly good among all the candidates in storage, but shows very bad cycling performance, which makes it not viable. Among the good cycling electrolytes, we can identify, we can see that they have low surface areas of lithium deposition, but very fast corrosion kinetics. But what we really need to make lithium metal anodes more viable are lithium metal chemistries that have low surface areas and slow corrosion kinetics, in addition to having good cycling stabilities. And basically, this kind of study guides the field in the kind of electrolyte design principles that we need to make lithium metal commercializable. And this kind of, we don't know the solution yet, but it may require some complex salt and solvent blends, or maybe even necessitate solid state electrolytes as well. And basically, just to recap everything we've seen today, what I've done is I've used cryo-TEM to identify how FEC stabilizes the silicon anode. And then I showed how cryo-STEM can give new insight into the real SEI structure and how classic characterization methods like XPS can give you completely wrong results if you're interested in what the SEI actually looks like. And finally, with cryo-TEM, we can identify the source of this rapid storage loss in lithium metal anodes. But broadly, the common theme across all of this work is that this new technique of cryo-TEM can really revolutionize our understanding of the structures within batteries. And there's still a ton of information to be uncovered within the field. And basically with this technique, we are starting to achieve kind of step function gains in insight for the real structures and chemistry within the battery and its SEI. Okay, so I've been very lucky to have what I would consider a good graduate school experience, and that's the sum of many people's contributions. First, my advisor, E. He's a really motivating guy, and he's obviously accomplished a lot. But what I like the most about E is that he has a lot of fun doing it. And he's taught me a lot about science, and I think most importantly, how to not only do good science, but also highly efficient science. And E is also he's really good about steering us away from research directions that are possibly unfruitful or overly complex, but still allows us to pursue our own interests. And for that, I'm very glad I chose to join E's group. And he also throws great parties as well. My two biggest mentors during grad school have probably been Yuzhong Li, who's now a professor at UCLA, along with Alan Pei, who now works at Tesla. So Yuzhong and I have spent many hours working together on the TEM, and he's taught me a lot about how to think about research and how to contextualize my findings. And Alan, we've had some very insightful discussions in graduate school, and he's taught me a lot about electrochemistry, writing papers, and has just been an excellent resource to bounce ideas off of. And I think the three of us also just had a lot of fun in lab together. I also had really great collaborators throughout graduate school, and all of these people have been really instrumental in getting all of this done and published. So in particular, I've worked closest with David Boyle, Peter Tia, and Hansen, who I have or will publish co-first author papers with. And the rest of the Tsui group has been really helpful as well. I've had great conversations and interactions with many members not listed in that previous slide. I also want to thank my committee members, Will Chu, who has been close to a co-advisor for me at times, and always impresses me with the depth of his insight. Bob, who taught me all of my TEM theory, and he was a lot of fun to hang out with at the microscopy conference in Portland a few years ago. Jinan and Jian, who we have regular joint meetings with, and always seem to return paper revisions really quickly and with a lot of detail. The SNSF staff, in particular the SEM and TEM staff, who help keep everything running, and all of them are extremely knowledgeable and helpful about microscopy, vacuum science, and electron matter interactions. Roy is no longer here, but him and I spent a lot of time working on the Titan together. And the GLAM and MSc staff who help keep research running and make sure we get paid on time. And a lot of those close collaborators from before are also good friends, and I've really enjoyed getting to know my lab mates outside of lab. One of the main reasons I joined the Tsui group was because of the fun atmosphere and the fun students and postdocs in the group, and I've never regretted that decision. I'm also lucky to have a really great cohort in the math sci department, and all of these people were really instrumental in getting through the coursework at Stanford and just overall like the early years of my graduate career. And without them, I probably wouldn't have passed my qualifying exams. And these people are all incredibly smart and fun, and together we've had really great experiences, and I look forward to many more. My family as well. Without my father, stepmom, and sibling support, I definitely couldn't have made it to Stanford in the first place. And for that, I'm incredibly grateful as well. And it's been difficult not being able to see them as much during the pandemic, but I'm glad that we've been able to spend almost every Christmas together while I've been in graduate school. And lastly, my wife, Lisa, has been my biggest supporter throughout the entire journey. And in a way, this is also her journey as well. And I'm so glad that she took a chance to follow me from San Diego all the way to Stanford. And her behind the scenes support has really helped make me into the researcher I am today. And with that, we can go back to the technical content, and I am happy to take any questions.
Well, thank you very much, Will. This reminds me how slow I am in revising the papers. Zhenan and Jen always fast. Let's open this up for questions. Maybe committee will ask in the closed session. We'll open it to the public first. Well, Bob, you have the burning question, sounds like. You're on mute, Bob.
Thanks, thanks, Yi. I just wanted to have a clarification question, and maybe a question which is related, which is broader than what I would ask in the oral exam, which was, you know, from the electron microscope field point of view, when you say cryo-EM, that normally a biological microscope of which there are hundreds across the world, and as far as I know, they can't do STEM or eels or anything. Whereas towards the end of your talk, you implied that, well, maybe you weren't using a traditional cryo-EM, you were using a physical science TEM and using a cooling holder. Now, is what I'm asking correct, or?
Yeah, yeah. So that's a very good point that should be clarified. And I didn't go too much in detail on the actual instrument that was used in all this characterization. But basically, you are correct that most cryo-EM, in the sense of the biological perspective, is done on microscopes that are designed for the purpose of high throughput biological samples, meaning that they don't have spectroscopy, they don't have a lot of them actually have the STEM unit, so the scanning unit, but they don't have STEM detectors. Basically, they're set up, purely to load biological samples quickly and take images quickly without any concern for spectroscopy. All of this work is done on a material science TEM with the addition of a cryogenic cooling holder. So the cooling holder basically makes the physical science TEM work for cryo-TEM, but then we get all the advantages of the material science TEM, which is the spectroscopy and the scanning TEM. So all of this work really can only be done on a material science TEM. And a dedicated biology cryo-TEM can have advantages in the sense that they can have somewhat higher sample throughput, but the depth of your characterization is just not going to compare to a real material science TEM.
Well, Will, just to clarify, this is mostly done on Titan, like the Titan we have here.
Yes, so all of this work is done on the Titan ETEM at SNSF.
So then a related question is, why would people even use a cryo-EM? Because you've shown such beautiful results showing the application of a physical science TEM with a cooling holder. So what's your impression as someone who's worked in the field now for several years about developing cryo-EM type technology for physical science work?
I think dedicated biology cryo-TEMs do serve some advantages in the sense that they are highly optimized for throughput. And a lot of them have very nice detectors equipped on them. So for example, the cryo-TEMs at SLAC are equipped with state-of-the-art direct electron detectors, which only recently we were able to get on the Titan ETEM, the material science TEM at SNSF. But the main advantage that I've seen from those cryo-TEMs as opposed to material science TEMs is they have autoloader technology, which allows you to basically swap through, I believe, a cassette of, I believe, about 10 samples without having to break vacuum, meaning that in a single day, you could probably get through all of your samples, whereas for a side entry TEM, using this kind of cryo holder in a material science TEM, you could maybe get through 3 or 4 samples if you are fast. So if you are willing to work with the cryo-TEM, and if you accept that you can't get spectroscopy, you can still get very nice images because you can get because they're equipped with very nice detectors. So for pure imaging, there still is some advantage to using a cryo-TEM, but for depth of analysis on a single sample, the material science TEM, I think, is more advantageous.
Okay, thank you.
Any other questions? This is your good last chance to ask Will before he will go to work outside to make millions of dollars in the industry.
Hey, Will, fantastic talk. I had a super quick question. I was just curious if you had any perspective on the role of FEC. It seemed that when added to the silicon anode, it produced a more amorphous layer. But when added to the lithium anode, it produced a more crystalline lithium oxide layer. And I didn't know if you had a theory for that or if it was dependent on the voltage of SEI formation or something.
Yeah, that's a very good question. And that's something I've spent a lot of time thinking about. So like what Harry is saying is that in the silicon case, when this lithium metal study here and the silicon study both use the exact same electrolyte. That's the 10% FEC in ethylene carbonate and diethyl carbonate. But the SEI nanostructure changes significantly between the two. In the silicon case, we see that there's a fully amorphous SEI, but with lithium metal, we see this kind of lithium oxide grains embedded within. And the reason why is, what we established previously is basically this lithium oxide is coming from ethylene carbonate reduction. And that's because in the silicon case, in the silicon study, we can see lithium oxide only when there's no FEC. So the difference then comes from the potentials that lithium metal sees and a fully lithiated silicon anode sees when it's lithiated down to 10 millivolts are about the same. It's about 0 volts versus lithium versus 10 millivolts versus lithium. That's a 10 millivolt difference. So it's likely not due to the reduction potential. I think the main difference is that when you are forming an SEI on any lithium ion battery system, whether it's graphite or silicon, you're bringing down the potential of the surface in a controlled manner, so somewhat slowly. During formation, you would do this at maybe like 1/20th of the nominal electrode capacity. So you're basically sweeping the potential from open circuit down to the lithium potential very slowly. When you're plating lithium metal, what you're doing is you can't do that kind of formation protocol since there is no host. Instead, what you're doing is you're forcing a current and you're basically creating this new lithium surface that's extending into the electrolyte. And that's basically equivalent to doing like a potentiostatic hold on like any other system. So rather than seeing the potential sweep down slowly for the electrolyte sees this 0 volt surface basically growing into the electrolyte. That means that you don't get any of that, you don't get as much of that preferential reduction where you first decompose the FEC, then you decompose the EC. Instead, you're decomposing everything at once. And the kinetics of the FEC will decompose faster because there's a higher overpotential because it wants to decompose first. But you're still decomposing everything together. And that's why you get this kind of more composite, more disordered SEI that's going to not only have the FEC, but the EC contribution as well. Does that make sense?
Yeah, that makes a lot of sense. Thank you very much.
Okay. If without further question, let's thank Will again, and also thank everybody for attending his thesis defense. Thank you, Will.
Okay, yeah. Thank you, everyone. And then the committee and I will go to the private session now.
Yeah.